I could write the result first and then we prove it, okay? Instead of, because these expressions are right in front of us, I would like to mention the final result that I am going to get. Final result I am going to get is del tau of pi mu tau plus del sigma of pi mu sigma. This object would be 0. We will prove it, okay? That this, and this in fact would be the equation of motion for the action. This in fact would also be the equation of motion for this action, and this is what we are now going to prove. Here it looks quite obvious, even if we do not do it term by term. If you take the time derivative of this, and if you take the space derivative of this object, and if you add up the two, this will come out to be 0. Okay? This will come out to be 0. And this we claim to be the equation of motion for this particular action. All right? So now, I mean, this is one way of verification. This is not a proof of this equation. Proof we are going to take up now. Okay? But this statement nevertheless can be verified with these two objects you have here, and you have pi mu of tau or pi mu of sigma. Take its time derivative, take its space derivative, add up the two, and this should give you 0. Okay? And now we derive independently again the so-called ab initio approach. We again from the variational principle. So for the time being, I remove this, and these expressions are there with you. So all right. So we have action of the theory. We have or we take delta S. This is your d2 sigma delta of L, and L is a function of x mu dot and x prime mu. Okay? And so you take it, L is minus T times the determinant of G alpha theta. Okay? So what we do is, this is minus T d tau d sigma times del L over del x mu dot into delta x mu dot plus, let me remove this L, we know it already. So plus del L over del x prime mu times delta x prime mu, and these two objects we would recognize that this would be pi mu of tau, and this object would be pi mu of sigma. Just for our records, let me write it here, d2 sigma into pi mu tau delta x mu dot plus pi mu of sigma let me write it more properly. Pi mu tau tau times delta x mu dot plus pi mu sigma delta x prime mu.
The indices should be different.
I made some mistakes.
On pi,
Yeah.
the mu should be downstairs.
Oh yes.
Well, yeah. Doesn't matter.
Yeah, only
Doesn't
one
matter.
has to be.
Yeah. And the other one.
Yes, correct. Okay, good, very good. Now, so now what we do is, again we use our usual trick. Basically, we transfer this to the other variable, and we transfer this to the other variable. So this x mu dot is your x mu dot is delta of x mu dot is delta of del tau of x mu, and this is del tau of delta x mu, and we do the same thing with delta x prime mu is delta del sigma of x mu. This is del sigma of delta x mu. So we use our standard trick, and this is a conventional trick being used in field theories all over. String theory is also string field theory. So you convert them into, you take one partial integration and you throw away the total time derivative term. That's the physically you say. So now del tau of pi mu tau delta x mu is equal to pi mu tau into del tau of delta x mu plus delta x mu del tau of pi mu tau, and therefore we are interested in which term. In this term is then equal to this minus that. Okay, so pi mu of tau into del tau of delta x mu. This is del tau of pi mu tau delta x mu minus delta x mu del tau of pi mu tau, and similarly we can write pi mu sigma del x mu equal to del sigma of pi mu sigma del x mu minus del x mu del sigma pi mu sigma. And we can then substitute for these two terms. We have one term here and one term here, and we want to, we would substitute this value here, and we will substitute this value here, and so we would have these four terms on the right hand side. Okay, and it's very clear to us that eventually this is a total derivative term. Its integration with respect to tau would give me only this evaluated at the time boundaries, and this would vanish. And here also this is a total derivative, and so when it is integrated with respect to sigma would give me this term, this value, which is to be evaluated at the sigma boundaries. And we would again use those tricks that these sigma boundary terms they would vanish either because delta x mu would be 0, or which is the case for the Dirichlet boundary conditions, or if that does not happen, delta x mu does not vanish. For Neumann boundary conditions, delta x mu does not vanish. X mu is allowed to shift around, okay, to move around. So in that case, we make them vanish by imposing x prime equal to 0. That's the space derivative of that. And you would notice from you have the full expressions of these objects here. These and these two objects, you have the full expressions, and you know that there is one x prime mu hanging around there, free x prime. So you will have it product of x prime mu into delta x mu. So this product x prime mu into delta x mu in any case would vanish. And for the closed boundary conditions, for the closed strings, it is again going to be the same. The story would be exactly repeated, and so all these sigma and tau boundary conditions would vanish. Tau boundary conditions vanish on their own, and sigma boundary conditions do not vanish on their own, but we make them vanish because we are motivated by those two kinds of things, where in the Dirichlet boundary conditions, delta x vanishes because x remains fixed at a point. So delta x is 0. Variation is not allowed. For Neumann boundary conditions, variation is allowed. X is not fixed. X itself can move around. It can fluctuate here. Okay, x can fluctuate here, this coordinate.